I hope you're doing well. So welcome to the very first session of Finite Element Analysis using SolidWorks. In this course, we will be learning how to perform various types of FEA analysis according to the problem which is given to us. And we will be doing all these analysis work using the SolidWorks simulation software. So the table of contents for the week were, first we'll learn what FEA is, and then we will look at the different types of analysis methods. The first one is the analytical method, the second one is the experimental method, the third one is the numerical method. And after that, I'll give you a brief explanation of FEA with the help of a cantilever beam. And then we'll talk about the stress and strain plot. And after that, I'll give you the general steps which are followed in solving any FEA. And we'll just talk about the mesh elements, the H refinement, the P refinement. In the end, I'll talk about the different types of analysis which is covered in the course, and just we'll have a summary. So before we jump into the software part, let us first understand what finite element analysis is and why do we use it. In simple terms, finite element analysis, which is abbreviated as FEA, is just one of the many methods which is used to solve engineering problems. To show you how FEA differs from other methods, let us first look at the more traditional methods of solving problems that you guys might be already aware of. So there are three main methods for solving engineering problems. The first one is the analytical method, the second one is the experimental method, and the third one is the numerical method. So let's talk about each of them now. So the first one is the analytical method. One of the ways of dealing with engineering problems is the analytical approach. And you would probably be more familiar with it since this is the approach followed for most of the problems you solve in school or college. An analytical approach is when you are given a problem with all the inputs or initial conditions, and then you use a set of mathematical formula which you either derive yourself or you directly use the formula some researcher has already derived. And then you just solve those mathematical equations to get the final answer, which would also be the solution to your engineering problem. A very basic example of analytically solving something would be, let's say I just drop a ball from the top of a 100-meter building and I ask you how much time it would take for the ball to reach the ground. So in this case, your initial conditions would be the initial velocity, which is 0, the height of the building, which is 100 meters, and the acceleration due to gravity, which is 9.8 meters per second. And to solve this, you don't need to derive any equation since Isaac Newton has already done the job for us. You would directly use the Newton's equation of motion, input the values, and get the final answer, which could be the time it takes for the ball to drop. So this is called an analytical way of solving the problem. As long as the formula you are using correctly represents the situation, the final answer which you get would be very accurate, but there are some problems that might occur in this approach which we will look into in a short while. Another way of arriving at the solution to any problem would be the experimental approach. So here, as the name suggests, you will carry out actual experiments and record the results to get the solution. So if we take the previous example of a ball dropped from a building, then someone would have to throw a ball from a height of 100 meters and someone would have to record the time it takes for the ball to reach the ground using a stopwatch. So here, as long as the experimental setup is correct and there is no issue with the recording device, the solution would be accurate. But even in this method, there are some issues which might arise, which we will take a look in a short while again. And one more method that can be used to solve engineering problems is the numerical method. The numerical methods are mathematical tools used to acquire approximate solutions to the problems. Now, some of you might wonder how we can get solutions to a problem using approximation. So to explain this, let's take a very simple problem. Here we have a circle, and let's say I want to know the circumference of the circle. But I don't know any formula related to finding the circumference of the circle. So here I can place straight sticks along the circumference of the circle, and then I can measure the length of just one stick and multiply that length with the number of sticks which I have to get an approximate circumference of the circle. It is true that you won't have an 100% accurate result in this case, but you can get a much more accurate result by reducing the size of the sticks and also increasing the number of sticks. Another example would be, let's say you want the area under this curve, but you don't know anything about integration. So one way to deal with this would be to divide the area under the curve into multiple rectangles, and then you can calculate the area under the rectangle to get an approximate area which is under the curve. Similar to the previous problem, more the number of rectangles, the more accurate would be the result you get compared to the true value of the area which is under the curve. So there are probably 2 points which you might have noticed. One is that even if you don't have a proper formula for solving something, you can still get an approximate solution using numerical methods. And the second is that the solution you get from numerical methods is not the exact true solution, but still it is very close to the true solution. So all of these 3 methods have some advantages and disadvantages, and the use of one of the methods would be preferred over the others based on the situation. So to get a better understanding of how these methods translate to engineering problems, let us also take up another very simple engineering problem that you guys probably would have come across. So this is an image of a cantilever beam. A cantilever beam is basically a beam which has one side fixed and the other side is free. So here I would like to check what would happen to the beam if I apply some force at the free end of the beam. And when I say I want to check what would happen, I specifically want to know how much the beam would displace from the default position after the load is applied. So first let's see how we can analytically solve this problem. Again, luckily for us, we have a differential equation which describes how the cantilever beam will behave when acted by a force, since someone has already derived the flexure formula. But it's important to note that there are some basic assumptions made while deriving this equation. So it only holds true as long as our case falls within those assumptions. So here I is the moment of inertia, E is the Young's modulus, and M is the bending moment of the beam. And if you want to find the displacement of the beam using this formula, then you will have to get the value of the variable y in the equation. So since we have the variable y in the second derivative form in the equation, we will have to integrate the equation 2 times to get the value of y. After the first integration, you will get something similar to this equation. You can get the value of constant by putting some boundary conditions. In this case, dy by dx represents the slope of the beam. And since at the fixed end there is no deflection, we could input dy by dx as 0 at the fixed end of the beam to get the value of C1. And then we will be integrating it again to get the equation in terms of y. Again, the displacement at the fixed end would be 0, and you can use that fact to get the value of the second constant. And finally, you will have an equation for the displacement of the beam. Substitute the values for known constants and you will get the final answer. So this was the analytical way of getting the displacement. If you want the same answer using experimental approach, then you would have to set up this model with proper dimensions, apply the correct force, and then you can manually check the displacement of the beam. Now let's look at how we would solve this problem using a finite element analysis. To solve this using FEA, we will have to split the entire beam into a number of smaller elements. For the sake of explanation, let's assume we split the beam into just 2 parts. In actual analysis, this beam can be split up to thousands of smaller parts. Here, each division is called an element, and the point between each division is called a node. Now to check the displacement of each of the beam, a simple equation called F equal to Kx is used, where F denotes the forces applied on the beam, X is the displacement we want to find, and K is the stiffness of the beam, which is basically a measure of how resistant the beam is to deflection under forces. To get these values, matrix calculations are used, as the software cannot solve differential equations. First, the value of stiffness K are found for each of the elements using a formula similar to what's shown on the screen. Using these individual stiffness matrix for the entire beam is formed, which is known as the global stiffness matrix. And then by using basic relation, previously shown, the displacements for the beam is calculated. In the displacement matrix, you can see two types of variables used, V and theta. The variables V1, V2 and V3 are supposed to give the linear displacement in the y direction for the nodes 1, 2 and 3 respectively, and the variable theta gives the angular displacement of the beam. So now that you know how to approach this problem by various methods, if I ask you to solve a similar problem, I'm sure most of you would prefer to go with the analytical approach, as it seems pretty straightforward with less calculations. And I agree that by just looking at this specific example, FEA might seem like an unnecessarily complicated approach to the problem. But a point to note here is that all the calculations involved in FEA are not manually done by us. All the calculations are done by the software. We just provide the model and the initial conditions for the software to run the calculations. And the second one is that the analytical approach seems significantly easier here, only because we already had an equation describing our setup and we didn't have to derive anything. Still, I would agree that using FEA for this problem is a bit of an overkill and we don't really need to use it. But then again, this is hardly a problem that an actual engineer would face while working in the industry. So why don't we look at how these methods hold up for real engineering problems? Let's say you are given a situation where a specific car model hits a wall at the speed of 120 kilometers per hour. And your task is to find out upon a crash how much of the passenger's compartment is damaged. The main goal is to minimize the damage as much as possible to ensure passenger safety. Now think about how you would solve this problem using the analytical approach. Heads up, there are no direct formulas which give the intrusion value for all car models ramming a wall at 120 kilometers per hour. I'm sure you can start noticing the problem with the analytical approach here. It is easy to deal with simple problems using an analytical approach, but as the complexity of the model increases, coming up with analytical solutions to a problem becomes significantly more difficult. Not to mention, while doing this crash test, there are multiple prototypes where the design and position of various parts will be altered. So you would have to come up with multiple analytical solutions. Even the experimental approach is unreasonable. Since you can't expect a new car to be made for every small design change and then crash all of those cars, the crash tests which you see are usually the final models of the car, which have already gone through many design alterations. So this is where FEA comes in. These types of analysis can be easily performed using many FEA softwares. You just need a 3D model of the car. You need to input all initial conditions and just let the software run the analysis. If there are any modifications in the design, you just need to add that change in the existing model. If there is any change in the test conditions, you just need to change the input conditions accordingly and the software will get the job done. So not only can you save a lot of time doing FEA analysis, you would also be saving a lot of money that would go into creating multiple prototypes. But here it's important to realize that FEA is still an approximate solution and may vary a lot depending on how accurately the test has been carried out. So even for a car crash analysis, once a final model has been decided, after running multiple simulations, an experimental setup is done with the final model to verify the results of the simulation. So now let's take a look at the topic of stress-strain plot. This graph which you see on your screen is a stress-strain graph for steel. On y-axis you have the stress values and on the x-axis you have the corresponding strain values. And these graphs are material specific, which means that for another material such as gold or copper, you will have different values. Now these graphs are all plotted through experimental results. So the way this works is, if you want a stress-strain graph for steel, then a steel rod will be selected and it will be subjected to tension loads to increase the stress of the steel rod. And they will keep increasing the stress value till the material breaks, and during the process a device will be used to keep track of the strain values in the rod. Then using all the stress and strain values, the graph is plotted. Now you might wonder, why do we need these plots? These plots help us in knowing how the material will behave when we apply load on any structure. Using these graphs, we can know if the load applied on any structure is safe or not. Also, when you perform any type of analysis in the software needs to be provided information regarding how the material will behave when a load is applied. If we apply a load of 100 Newton on a steel beam, or if we apply 1000 Newton, then the simulation results will obviously be different. But the software is able to create a proper simulation for the material because the information of stress strain plots are already added to the software. So a user would just select the material for the model and the software will predict accurate behavior based on these experimental results. Now there are a few important points in the stress strain plots which we will be discussing about. Initially, when the material is subjected to stress, the deformation or the strain which the material experiences is directly proportional to the stress values. This is represented on the plot by a straight line between points O and point A. Mathematically, stress would be equal to some constant multiplied by strain in this region. This mathematical equation is called as the Hooke's law. And the point A, which you see at the end of the line, will be called the proportional limit of the material, since stress and strain are found to be proportional to each other between points O and A. Another thing to note is that as long as the strain in the material is between these points O and A, the deformations in the material are elastic in nature. This means that if the material has a strain value below point A, then if you remove the load on the material will go back to its original shape. Similar to how a rubber band goes back to its original shape once you stop stretching it. Once the stress values exceed point A, the material will no longer obey Hooke's law, which means that the strain in the material will no longer be proportional to the stress value, and you can see that represented by a curve. But even between the regions between point A and B, the deformation is still elastic in nature, and if the load is released, the material will go back to its original position. But point B on the graph is the region after which the plastic deformation starts. So if you apply a stress value higher to the value corresponding to point B, then even after removing the stress, there will be some permanent plastic deformation in the material. This point B after which the plastic deformation begins is known as the elastic limit or the yield point of the material. After point B, you will notice that the graph has flattened. So in these plastic regions, even for very small increases in the stress value, the material deformation is very high. And this continues up to point C. So the point C at which the material starts breaking is the highest stress value that the material can withstand and is hence known as the ultimate tensile strength of the material. And if any metal is subjected to a very high stress, it doesn't immediately snap into two pieces. There is a gradual decrease in the cross-sectional area as shown in the image before the material completely snaps into two pieces. So this decrease in cross-sectional area will begin at point C, which is the ultimate tensile strength. Then the material will completely snap into two pieces at point T, which is called the fracture or the breaking point of the material. Here we will discuss the three main steps which are part of any analysis done using the FEA method. And to better understand what exactly happens in each step, we will be using the car model which we were discussing earlier. So the first step in any FEA analysis is called as pre-processing. Since FEA is used for analysis of a product, before we can get into using FEA, we need a CAD model of the product we are analyzing. So before we start pre-processing, we will be given a CAD model which we will be importing into a pre-processing software. After importing the model, we usually perform a quick check to verify that there is no issues with the model. Sometimes when you import a model into a different software, some issues like gaps in the model and self-intersections occur. But most of these issues can be easily fixed using automatic tools in the software. Once it is verified that there are no issues with the model is discretized into a number of smaller elements, similar to what we had seen in the cantilever beam example. And depending on the type of analysis, there are various quality parameters which the individual element must fulfill. So some quality checks are also performed after discretization to ensure that the mesh is good enough for the analysis. But since this is an introductory course into FEA, we won't be going into details of mesh quality parameters in this course. And in the end, we have to define the conditions of simulation that we want to run. This includes all the details regarding which parts of the model is fixed, where the loads are applied in the model, the values of the load applied, initial conditions of the model, the material of the model, etc. There are many softwares available for pre-processing such as Hypermesh, Answer, Nastran, LS-Dyna, and many more. The next procedure is processing. The processing involves the actual running of the simulation in the software. There's not much to be done from the user side in this step. The software does all the mathematical calculations required for FEA in the backend, and the output will be the simulation of the test being performed. Software such as Autodesk Simulation, ANSYS are usually used for processing. And in the end, we have post-processing. Post-processing basically involves the visualization of the data obtained from the simulation. And based on what the objective of the study was, you would either verify your hypothesis or select the best design. Or you could recommend some changes in the design based on the results which you got. So we had previously discussed that models which work on using FEA are discretized to a number of small elements. This process of discretization is known as meshing. There are two types of element shapes that are generally used, the triangular element and the quadrilateral element. In basic triangular element, we would have 3 nodes, as you can see in the image, and in the quadrilateral element, we would have 4 nodes. The type of mesh selected depends on the accuracy of the result required and the computational time allotted, and thus may vary according to the application for which the meshing is done. In structural problems, we usually go for quad elements. For crash and non-linear analysis, we try to go for the quad element, but some triangular elements may be necessary to capture the model properly. And for casting simulation, triangular elements are preferred over quads. Any model that we will be using for FEA analysis will consist of intricate shapes and profiles that cannot always be properly captured even after discretizing them. So the more complex the model is, the more is the number of elements used in order to get an accurate result. The process of discretizing the model more by reducing the size of elements and increasing the number is known as refining the mesh. So in order to check whether discretization, which we have done, is sufficient or not, we perform something called the grid dependency test. In grid dependent tests, we basically run the same simulation multiple times by refining the mesh up to a point where the result does not change even after refining the mesh further. In order to refine the mesh, there are 2 methods which are generally used. First is the H refinement and the other one is the P refinement. So to understand how these 2 methods vary, let us look at this model which is already meshed. So if I want to refine this mesh using a H refinement method, then I would just directly increase the number of elements in this grid. More the number of elements, more would be the number of calculations over a short distances, and thus the result I would obtain in this new mesh would be more accurate. If I want to refine the same mesh using P refinement method, then instead of adding new elements, one can also increase the number of nodes in the mesh. While running any FEA simulation, the various displacement values are interpolated using some functions which are known as shape functions. So by increasing the number of nodes, you increase the order of these shapes. Higher the order, more accurate is the result of the simulation. Now we will take a look at the types of analysis that are available in the SolidWorks software. We will just be giving a brief explanation here, and in the further sessions we will go into a bit more detail. So the first one is the static analysis. As the name suggests, static analysis is used in places where the forces, load, acceleration and many other initial conditions which are applied do not vary with time. So as long as the constant load is applied, static analysis can be used to check the stress, strains or displacement in various models subjected to various forces. The cantilever beam, for example, which we saw at the beginning, would be an example of static analysis. Then the next type is the fatigue analysis. This applies for machines or components which are subjected to loads regularly after fixed intervals of time. When a material is subjected to loads again and again for long duration, then the material becomes weak and usually fails at stresses lower than its ultimate tensile strength. So to deal with such situations, where you would like to know how long the component will last, one can use a fatigue analysis. Next is frequency analysis. Whenever any object is subjected to any force, there is vibration in the object, and every object vibrates at a fixed natural frequency. In certain types of problems, which we will look into in further sessions, it becomes important to know what the natural frequency of the object is. So to find the natural frequency of any model, frequency analysis can be used. Then we have the buckling analysis. Buckling is a type of material failure which usually occurs when long members are subjected to compressive loads. If you have a vertical column fixed at both ends and you keep increasing the load, there is a chance that after a specific value, you will notice a sudden change in the shape as shown in the image. So buckling analysis, you can visualize this process and check the load values at which the buckling would occur. And in the end, we have drop test. As the name suggests, this type of analysis is used for checking the impact on any component if it is dropped from a certain height and velocity. This is usually used for electronic components and gadgets such as mobile phones. So after running this analysis, you can check which places on the object are subjected to more stress, and you can make the design changes accordingly. So that's it for this session. So let's have a quick summary. So in this session, we saw the various methods of solving engineering problems such as analytical, experimental, and numerical methods. We learned about the general steps in FEA, which are pre-processing, processing, and post-processing. Then we saw what is meshing and how to refine it. And in the end, we saw the various types of analysis that can be performed in SolidWorks.